In this lecture, I'll answer two questions. In the first question, you find out the radius of this circle that blocks quadrilateral ABCD. And in the second question, you find out the length of this line segment AP that is equals to x. We have to find out the value of x. So let's start with the first question. In the drawing, we have a quarter circle that is inscribed by this circle. In addition, we know that side AB of quadrilateral ABCD equals to side BC. We also know that AC is the diameter of this circle. In addition, we know that the perimeter of this quadrilateral ABCD is equal to 18 units. That is to say, the sum of its four side lengths is equal to 18. AB plus BC plus CD plus DA in total is equal to 18. And we also know that the area of this quadrilateral ABCD is equal to 16 square meters inside. Again, our task is to find out the radius of this circle. So, first of all, we will define the sides of quadrilateral ABCD with letters. That is to say, we define the length of side AB as A. AB equals to A units in itself according to our definition. And because of the fact that side AB equals to side BC in itself, the length of BC must be also equal to A. We define the length of side AD as B. And finally, we define the length of side CD as C. So here we can implement rule 7 in our drawing. I repeat quickly on rule 7. According to rule 7, if a peripheral angle subtends on the diameter of the circle, then it is equal to 90 degrees in its size. In the drawing, we have a circle. This is peripheral angle ACB that subtends on chord AB, that is the diameter of this circle, and therefore peripheral angle ACB is equal to 90 degrees in its size. So, according to this rule 7, any peripheral angle that subtends on the diameter of the circle must be equal to 90 degrees in its size. So we can actually implement rule 7 in our drawing. In our drawing, we have, this is peripheral angle ABC that subtends on chord AC, that is the diameter of this circle, and therefore peripheral angle ACB must be equal to 90 degrees in its size according to rule 7. Likewise, this is peripheral angle CDA or ADC that subtends on the same chord called AC, that is the diameter of this circle, and therefore according to rule 7, it must be equal to 90 degrees in its size. In the next step, we will implement the Pythagoras theorem on those two right triangles. On the right, this right triangle ABC and this right triangle ADC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in the right triangle ABC, here by PT is evaluation for Pythagoras theorem. So in the right triangle ABC, AC squared, that is the square of the hypotenuse, is equal to AB squared plus BC squared. And again, in the right triangle ABC according to the Pythagoras theorem, and get that AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. AC is the missing side, so we know the CT, so it is AC squared equals to AB squared. AB is A, therefore AB squared is A squared plus BC squared. BC is also A, so BC squared is A squared. So in total, je found out that AC squared equals to A squared plus A squared, that is 2A squared. So AC squared equals to 2A squared. This is according to equation 1, this is equation 1. So in the next step, we implement the Pythagoras theorem on this right triangle ADC. According to the Pythagoras theorem, this right triangle ADC, AC squared, that is the square of the hypotenuse, is equal to AD squared plus DC squared. And again, in the right triangle ADC, according to the Pythagoras theorem, we get that AC squared equals to AD squared plus DC squared. AC is the missing side, so we leave it as it is, so it is AC squared equals to AD squared. AD is B, therefore AD squared is B squared plus DC squared. DC is C, therefore this DC squared is C squared. So in total, according to equation 2, I should found out that AC squared equals to B squared plus C squared. So we have two different equations for AC squared. Equation 1 that says that AC squared equals to 2A squared. And we have equation 2 that says that AC squared equals to B squared plus C squared. So in the next step, we have equation 3. It says that AC squared according to equation 1 must be equal to AC squared according to equation 2. AC squared according to equation 1 equals to 2A squared, and it must be equal to AC squared according to equation 2, that equals to B squared plus C squared. So in total, according to equation 3, we should find out that 2A squared equals to B squared plus C squared. So here we divide this equation 3 by 2. And finally we get that A squared equals to B squared plus C squared over 2. It is given as a equation that the perimeter of this polynomial ABCD equals to 18 units. That is to say AB plus BC plus CD plus DA in total is equal to 18. AB is A, BC is A, CD is C, and AD is B. So in total A plus A is 2A, so 2A plus B plus C equals to 18. So 2A plus B plus C equals to 18. It is given as a question that the area of this quadrilateral ABCD equals to 16 square units in size. Quadrilateral ABCD consists of those two right triangles, the right triangle ABC and this right triangle ADC. Therefore, the area of quadrilateral ABCD must be equal to the sum of the areas of the two shapes that it consists of. That is to say, it must be equal to the area of the first shape, that is the area of this right triangle ABC, plus the area of this second shape, that is the area of this right triangle ADC. So it is only found out that the area of quadrilateral ABCD must be equal to the sum of the areas of the two shapes that it consists of. The first shape that it consists of is the right triangle ABC, and the second shape that it consists of is this right triangle ADC. Okay, again, according to equation 5, the area of quadrilateral ABCD must be equal to the sum of the areas of the two shapes that it consists of. The first shape is the right triangle ABC, and so this is the area of the right triangle ABC, and the second shape it is the right triangle ADC. So plus the area of the second shape, that is the area of the right triangle ADC. It is given as a equation that the area of quadrilateral ABCD equals to 16 square units. Therefore, we substitute the area of quadrilateral ABCD by 16. And get that 16 equals to the area of triangle ABC, the right triangle ABC. What is the area of this right triangle ABC? The area of this right triangle ABC must be equal to the base AB times the height BC over 2. AB is A, BC is A, so it is A times A over 2. A times A is A square over 2. So in total, we should know that the area of the right triangle ABC equals to A square over 2 plus the area of the second shape that is consisted of the area of this right triangle ADC. The area of this right triangle ADC equals to the base AD, that is B, times the IDC, that is C over 2. So it is B times C over 2. So the area of the second shape equals to B times C over 2 square units in its size. So in total, we found out that 16 equals to A square over 2 plus BC over 2. Here we multiply this equation 5 by 2, and find again that according to equation 5, (16) times 2 is 32. And it is equal to A square over 2 times 2, that is A square, plus BC over 2 times 2, that is BC. So in total, according to equation 5, we actually found out that 32 equals to A square plus BC. While according to equation 4, we actually found out that 2A plus B plus C equals to 18. Actually, according to equation 3, we actually found out that a squared equals to b squared plus c squared over 2. And again, according to equation 3, we already found out that a squared equals to b squared plus c squared over 2. According to equation 5, 32 equals to a squared plus b c, while according to equation 3, a squared equals to b squared plus c squared over 2. So we actually can substitute a squared in this equation 5 by b squared plus c squared over 2 for this equation, equation 3. We do it now, we get that according to equation 5, 32 equals to a squared according to equation 3 is b squared plus c squared over 2, and we have also plus bc. So according to equation 5, we actually found out that 32 equals to b squared plus c squared over 2 plus bc. Here we multiply bc by 2 and we divide it by 2 in order to account for this expression, and we get that according to equation 5 in total 32 equals to b squared plus c squared over 2. Now we multiply bc by 2, so it is 2 times bc over 2. We multiply it by 2, then we divide it by 2, so we change nothing. So according to equation 5, we actually found out that 32 equals to b squared plus c squared plus 2 times b times c over 2. So here we multiply this equation 5 by 2, and finally we get that according to equation 5, 32 times 2 is 64 equals to b squared plus c squared plus 2 times b times c. So here we use the algebraic identity. It says that a squared plus b squared plus 2 times a times b equals to a plus b squared. So according to this algebraic identity, we get that b squared plus c squared plus 2 times b times c equals to b plus c squared, and it is equal to 64. 64, according to equation 5, 64 equals to b plus c squared. So here we take out all of this equation, and finally get that the square root of 64 is 8, equals to the square root of b plus c squared is b plus c. So total actually found out that b plus c equals to 8. Again, according to equation 5, actually found out that b plus c equals to 8. And according to equation 4, we only found out that a plus b plus c equals to 18. Again, according to equation 4, we only found out that 2a plus b plus c equals to 18. So, because of the fact that b plus c equals to 8, we can substitute b plus c in this equation 4 by 8 from equation 5. We do it now, we get that 2a and b plus c is 8 according to equation 4, according to equation 5, equals to 18. So according to equation 4, we found out that 2a plus 8 equals to 18. Here we subtract 8 from this equation 4, and finally get that according to equation 4, 2a equals to 18 over 8 is 10, so 2a equals to 10. Here we divide this equation 4 by 2, and finally get that a equals to 10 over 2, that is 5. So we should find out that a equals to 5 units in its name. So a equals to 5 units in its name. AB that equals to a equals to 5. And BC that is also equals to a equals to 5 units in its name. So in the next step, we implement the Pythagoras theorem on this triangle ABC. This triangle ABC, according to the Pythagoras theorem, AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. And again, according to the Pythagoras theorem, in this triangle ABC, AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. AC is the missing side, so we leave this it is, so it is AC squared equals to AB squared. AB is 5, therefore AB squared is 5 squared, that is 25, plus BC squared. BC is also 5, so BC squared is 5 squared, that is 25. So in total, if you found out that AC squared equals to 25 plus 25 is 50, so AC squared equals to 50. Here we substitute 50 by 2 times 25, or 25 times 2. So AC squared equals to 25 times 2. Here we take a lot out of the little equation, and finally we get that AC equals to the square root of 35, the square root of 25 is 5, so inside the root we left only with 2. So in total we should find out that AC equals to 5 times square root of 2 units in its name. AC is the hypotenuse of both right triangles, but AC is also the diameter of the circle. So we know that the diameter of the circle AC equals to 5 times square root of 2. And therefore, the radius that we are looking for in this question, we find the radius as R, so the radius R must be equal to the diameter AC over 2. That is to say, it must be equal to 5 times square root of 2 over 2. So in total, we should find out that the radius of this circle, that is the radius that we are looking for in this question, is equal to either 5 times square root of 2 over 2 units in its length, or in terms of numbers, is equal to 3.536 units in its length. And again, the radius that we are looking for in this question, this is the radius of this circle, it is equal to either 5 times square root of 2 over 2 units in its length, or in terms of numbers, the radius of this circle is equal to 3.536 units in its length. So, finished with the first question. The next step, I present you the second question and solve the second question of this lecture. The second question, our task is to find out the length of this line segment AP is equals to x. We have to find out the value of x. So in the drawing, we have the right angle ABC that blocks this circle, or this circle is inscribed by this right angle ABC. This is angle ABC, this is right angle. We also know that QS equals to 25, cos QP equals to 24. This is the tangent to the circle at this point, so define the point of tendency of this tangent to this circle. This point is point M. Again, SM is a tangent to this circle, it's point M. Our task is to find out the length of this line segment AP is equals to x. We have to find out the value of x. So first of all, we'll implement rule 2 in our drawing. Repeat quickly on rule 2. According to rule 2, the lengths of two tangents from common start point to a circle are equal. In the drawing, we have a circle. This is the common start point, point P. For this common start point, point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule 2, they are equal to each other. That is to say, the length of this tangent PA is equal to the length of this tangent PB, or PA equals to PB. So we can implement rule 2 in our drawing. Why? Because in our drawing, if you focus on this common start point, point A, from this common start point, point A, we have two tangents to the circle, tangent AP and tangent AQ. AQ is tangent to the circle at point Q. We have tangent AP and tangent AQ. According to all two, they are equal to each other. That is to say, AP equals to AQ, but AP equals to x, therefore AQ must be also equal to x unit in its length. Tangent AQ must be also equal to x units in its length. According to all two, of course. We will define the length of this short tangent BM as A. So for the common start point, point P, we have two tangents to this circle. Two tangents to this circle, tangent BM and tangent BQ. And according to rule 2, they are equal to each other. That is to say, BM equals to BQ. But BM equals to A, therefore BQ must be also equal to A units in its length. According to rule 2. In the next step, we'll focus on this common start point, point S. For this common start point, point S, we have tangent SM, that is tangent to this circle, it's point M. Likewise, we also have, this is chord PQ. The extended chord PQ touches point S. So all the requirements for rule 10 are satisfied, and therefore we can implement rule 10. I can click on rule 10. According to rule 10, rule 10 is true in any circle. In any circle, if AB is any chord in the circle, and PT is a tangent to the circle, then PT square equals to PA times PB. Again, PT square equals to PA times PB. So in the drawing, we have a circle, and this is the common start point, point P. From this common start point, point P, we have tangent PT. That is tangent to this circle, point T. Likewise, we have here, this is called BA. The extended chord BA touches point P. So in this drawing, the following equation is true, that PT square equals to PA times PB, and PT square equals to PA times PB. So can you implement rule 10? And this comes to point, point S. So as I mentioned before, all the requirements of rule 10 are satisfied. Well, because we have tangent SM, that is tangent to this circle at point M. And we also have chord PQ. The extended chord PQ touches point S. So all the requirements of rule 10 are satisfied and therefore can implement rule 10. According to rule 10, the following equation is true. That SM square equals to HQ times SP. Again, SM square equals to HQ times SP. Now write it down according to rule 10. If you focus on the common sense point S, the following equation is true. That SM square equals to SQ times SP. And again, according to rule 10, the following equation is true. And SM square equals to SQ times SP. SM is the missing tangent, so we leave it as it is, so it is SM square equals to SQ is 25 times SP in total equals to SQ, that is 25, plus QP, that is 24. So in total, SP equals to 25 plus 24, that is 49. And again, according to rule 10, SM square equals to SQ times SP. SM is the missing side, SQ is 25, and SP is 49. So in total, SM square equals to 25 times 49. So here we take out all of this equation. And finally we get that the missing tangent SM is equal to the square root of 25, that is 5, times the square root of 49, that is 7. So in total, SM equals to 5 times 7, that is 45. 5 times 7, that is 35. So tangent SM equals to 35 units in its length. This is tangent SM, is equals to 45 units in its length. What is the length of this missing line 7? Line 7 SB. SB in total equals to SM plus BM. So write it down. SB in total equals to SM plus BM. So SB equals to SM, that is 35, plus BM, that is 8. So in total, SB equals to 35 plus units in its length. This is line 7 SB equals to 35 plus units in its length. In the next step, we will implement the bottom one on this. So, we know that SM is a tangent to the circle at point M. So SM is a tangent, it is absolutely a straight line. So if we focus on the upper side of the straight line SM at point B, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 says that the sum of the angles from one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line SM at point B? We have this angle, that is the right angle. plus this vicinagel, total tillsammans dos frågas, man ska på andra degree, konditorskillnad for this vicinagel, man ska to 90 degrees in its size. And therefore, triangle SQB is the right triangle. So the next step, we implement the Pythagoras theorem on this right green triangle SQB. Here by PT is the version for Pythagoras theorem. So in this right green triangle SQB, SQ squared, that is the square of the hypotenuse, is equal to QB square plus BS square. And again, according to the Pythagoras theorem, this right green triangle SQB, SQ squared, that is the square of the hypotenuse, equals to QB square plus BS square. The hypotenuse QS equals to 25, therefore QS squared is 25 squared, that is 625. It is equals to QB squared. QB is 8, therefore QB squared is 8 squared. Plus BS squared. BS is 45 minus 8, therefore BS squared is 35 minus 8 squared. And so if you found out that 625 equals to 8 squared plus 35 minus 8 squared. So 625 equals to a square plus 35 minus a square. 35 minus a square equals to 35 squared, that is 1225 plus a square minus 2 times 35 times a is 178. So 625 equals to a square plus a square is 2a square, 178 plus 1225. Here we subtract 625 from the equation. So here we left with nothing, that is to say 0. And on the other side of the equation we have 2 times a square, 178, and 1225 from 625 is 600. So I'm going to find out that 0 equals to 2a square, 178 plus 600. Here we divide this equation by 2. And finally we get that 2a square over 2 is a square, 178 over 2 is 135a, 600 over 2 is 300, and 0 over 2 is 0. So in total, if I found out that a squared minus 35a plus 300 equals to 0. So actually this is a quadratic equation, and the general formula for quadratic equation is as follows: ax squared plus bx plus c equals to 0. In this general formula for quadratic equation, a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula: x equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. Another specific quadratic equation, that is to say a squared minus 45a plus 300, the variable that we are looking for is of course a. So x equals to a. The coefficient a equals to 1. The coefficient b equals to minus 45. And finally, the coefficient c equals to 300. So here all the data it is needed in order to find out the variable that we are looking for this quadratic equation is a. You just have to put the data that you have for this quadratic equation inside this general formula for x. In this way we find out the variable that we are looking for, that is a. So x equals to a, and it is equals to minus b. b is minus 35, therefore minus b is minus 45, that is plus 35, plus minus square root of b squared. b is minus 45, therefore b squared is minus 45 squared, that is 1225. We have minus 4 times a times c. a is 1, c is 300, so minus 4 times a times c is minus 4 times 1 times 300. That is minus 1200, so in total minus 4ac is minus 1200 over 2a. a is 1, so 2 times a is 2 times 1, that is 2. So in total we should find out that a equals to 35 plus minus square root of 1225 minus 1200 over 2. So a equals to 35 plus minus 1225 minus 1200 is 25, so inside the root we left only with 25 over 2. So here we have a equals to 35 plus minus square root of 25 over 2. The square root of 25 is 5, so in total we get that a equals to 35 plus minus the square root of 25 is 5 over 2. So here you will have two solutions that are possible for a. The first solution for a is that a equals to 35 plus 5 over 2. 35 plus 5 is 40, and 40 over 2 is 20. So the first solution for a is a equals to 20. And the second solution for A is that A equals to 35 minus 5 over 2. 35 minus 5 is 30, and 30 over 2 is 15. So the second solution for A is 15. Okay. Yeah, the next step, we'll do a construction. This is the green triangle AQP. The green triangle AQP is an associated triangle because side AQ equals to side AP. QP is of course the best of this associated green triangle AQP. So we do here a construction. That is to say, from the vertex A, we go perpendicular to the base QP. Again, from the vertex A, we go perpendicular to the base QP of this associated green triangle AQP. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A in the base QP. This point is point Z. So here, this is the associated line AQP. And from the vertex A, we go perpendicular AZ to the base QP. So here we can definitely implement rule 21. Please click on rule 21. According to rule 21, the perpendicular to the base of an associated triangle bisects the base. So in the drawing, the associated triangle, triangle ABC. Triangle ABC is an associated triangle because side AB equals to side AC. BC is of course the base of this associated triangle, triangle ABC. For the vertex A, we go perpendicular to the base BC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. So AO is the perpendicular to the base BC. And according to this rule 21, the perpendicular AO bisects the base BC. Again, the perpendicular AO to the base BC bisects the base BC. That is to say, divide this into two halves. The first half BO is of course equals to the second half OC. Each half must be equal to BO or to BC over 2 because the base BC has been bisected into halves. Each half, of course, must be equal to BC over 2. So BO equals to OC equals to BC over 2. So we can implement rule 21 in our drawing. We'll put in our drawing, we have the associated triangle AQP. We draw the perpendicular AZ to the base QP. According to rule 21, the perpendicular AZ to the base QP bisects the base QP. So the first half QZ, of course, equals to the second half ZP. Each half, of course, must be equal to QP over 2. So okay, now, so in the associated triangle, triangle AQP, according to rule 21, the perimeter AZ to the base QP bisect the base QP. So the first half QZ must be equal to the second half ZP, and each half, of course, must be equal to QP over 2. And again, according to Rule 21, the perimeter AZ to the base QP bisect the base QP. The first half QP must be equal to the second half ZP, and each half must be equal to QP over 2. According to Rule 21. QP is 24, so QP over 2 is 24 over 2. 24 over 2 is 12. From this long equation, we derive that QP equals to ZP equals to 12. QP equals to ZP equals to 12. QZ equals to 12, and ZP also equals to 12. Here it is QZ equals to ZP equals to 12. QZ equals to 12 and ZP also equals to 12. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. So if you define the size of this vertex angle as alpha, then the size of this vertex angle must also equal to alpha. So in this right rectangle, AQZ, this angle equals to alpha, this angle equals to 90 degrees, and therefore this furthest angle must be equal to 90 degrees once alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees is equal to 180 degrees, that is the sum of the angles in the triangle. Likewise, this small triangle QBS, this angle equals to alpha, this angle also equals to 90 degrees, and therefore this furthest angle must be equal to 90 degrees minus alpha, according to the sum rule that says that the sum of the angles in any triangle is equal to 180 degrees. It's very easy to see from the drawing that the right triangle AQZ is similar to this right triangle SQB, right triangle SQB, according to angle similarity rule. That is to say, those two angles are both equal to alpha, and therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees also alpha, and therefore they are equal to each other. So if you found out that all the triangles of this right rectangle QBS are corresponding equal to all the triangles of this right triangle AQZ, and therefore those two right triangles are similar to each other according to angle similarity rule. So write it down. If you found out that the right small rectangle QBS similar, this is the sign of similar to this right rectangle AQZ, counting angle similarity rule. And again, we found out that right grand triangle QB is similar to the right small grand triangle AQZ according to angle similarity rule. The right grand triangle small grand triangle QB is similar to the right big triangle AQZ according to angle similarity rule. And from the fact that those two right grand triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side SQ of this small grand triangle SQB or side AQ of this grand right triangle AQZ is equal to side QB of this grand small right triangle SQB or side QZ on this small right triangle in QZ. And again, from the fact that those two right grand triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side AQ of the right small triangle SBQ or side AQ of the big right triangle AQZ is equal to side QB of the small right triangle SBQ or side ZQ of the big right triangle AQZ. SQ is 25 over AQ. AQ is X, that is the value that we're looking for in this question. And it's equals to QB. QB is A over QZ. QZ is 12. So we found out that 25 over X equals to A over 12. Here we cross multiply this equation. And finally we get that 25 times 12, that is 300, is equal to 8 times X. 300 equals to 8 times X. Here we will divide this equation by A. And finally we get that X equals to 300 over A. So we have two solutions for A. A equals to either to 20 or to 15. So in the next step we'll find out what is the real value of A. In order to find out what is the real value of A is the length of BM and the length of QB. In order to find out what is the real value for A, is it 20 or 15? I copy this right triangle ABC with the circle that is inscribed inside it and a new drawing, and analyze the drawing in order to find out what is the real value of A. Is it 15 or 20? This is the right triangle ABC with the circle that is inscribed inside it, that according to the original drawing. So we already found out that AQ equals to X and QB equals to A. So in the next step we will find the point of tendency of the ABC with the circle. This point is point M. And define the center of this circle. This point is point O. We define the radius of this circle as R. And join points O and M together by straight line. Point O is the center of this circle. Point M is the point of the circle itself. Therefore, OM is the radius of this circle. This is equals to R. The radius OM is equals to R. The radius OM is known to point M. That is the point of tendency of tangent BC with this circle. And now, your radius is known to the point of tendency. Then tangent BC will be perpendicular to the radius MO. If BC is perpendicular to MO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to rule 1. Point Q is the point of tendency of tangent AB with this circle. In the next step, we join points O and Q together by straight line. OQ is of course the radius of this circle, equals to R. And according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. And this for the other Q, O, and B, we have 1, 2, 3 angles. And therefore this fourth piece here must be equal to 90 degrees inside. According to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. So in quadrangle Q, O, and B, we have 4 angles, and therefore can relate to quadrangle Q, O, and B is a rectangle. But you also know that the opposite sides of a rectangle are equal to each other. So this small rectangle Q, O, and B, side OM must be equal to the opposite side OB. But OM is R, it is the radius of the circle, therefore QB must be also equal to R in its length. So QB equals to, QB at the same time equals to A, and also equals to R. QB equals to A equals to R. In the next step, we will do a construction, that is to say, we will extend the radius MO by a straight line until it touches the circle. And we define the touching point of the extended radius MO in this circle. This point is point Z. OM is a radius, it is absolutely a straight line. We extended the straight line OM by a straight line, the result MZ must be also a straight line. So MZ is a straight line. If you focus on the right side of the straight line MZ at point O, here the sum of the angles must be equal to 180 degrees according to rule 3. So which angles we have at the right side of ZM at point O? We have this angle that is the right angle, plus this piece angle, in total must be equal to 180 degrees according to rule 3, therefore this piece angle must be equal to 90 degrees in size. In the next step, we will do another construction, that is to say from side AB, we will go tangent to the circle at point Z. Again, from side AB, we go tangent to this circle at point Z. We find the touching point of this tangent with AB. This point is point T. I repeat again, that TZ is a tangent to this circle at point Z according to our construction. Again, TZ is a tangent to this circle at point Z according to our construction. So here you can implement rule 1 because we have the radius OZ is the radius because point O is the center of the circle, point Z is the point of the circle itself, therefore OZ is the radius of this circle that equals to R. The radius OZ is equals to R, the radius OZ is known to point Z, that is the point of tendency of tangent TZ if this circle. Whenever your radius is drawn to the point of tendency, then tangent TZ will be perpendicular to the radius ZO. If TZ is perpendicular to ZO, it means that this again equals to 90 degrees according to rule 1. So in the upper quadrilateral, this upper quadrilateral TZ or Q, we have 1, 2, 3 angles. Therefore, this fourth missing angle must be equal to 90 degrees in size. And therefore, quadrilateral TZ or Q is a rectangle because it has 4 right angles. But we also know that the opposite sides of rectangle are equal to each other. So in the upper rectangle TZ or Q, side ZO must be equal to the opposite side TQ. But ZO is R, it is the radius of the circle. Therefore TQ must be also equal to R units in its length. We already found out that QB equals to A and QB also equals to R. QB equals to A, QB also equals to R. So I write it down. QB equals to A and QB also equals to R. What about assignment AQ? AQ equals to X from one side, but AQ also equals to AT plus TQ. Again, AQ in total equals to AT plus CQ. So AQ in total equals to AT plus CQ, but TQ is R, so therefore AQ in total equals to AT plus R. So AQ equals to X, AQ also equals to AT plus R. AT is a length. AT is a length, it is a positive number. AT is a positive number, and therefore AT plus R is definitely greater than R. Again, because of the fact that AT is a positive number, AT plus R, it is definitely greater than R. So we can write here that AT plus R is greater than R. And from this non-inequality, we get that A is smaller than X. A is smaller than X, or X is greater than A. So just right now found out that X is greater than A. And we have two solutions for A. A either equals to 20 or to 15. Either equals to 20 or to 15. Now we found out that x equals to 300 over a. Again, x equals to 300 over a. So it is done. Now we found out that x equals to 300 over a. Therefore, if a equals to 20, then x must be equal to 300 over 20, that is 15. So if you found out that if a equals to 20, then x must be equal to 15. Likewise, if a equals to 15, then x must be equal to 300 over 15, that is 20. So if you found out that if a equals to 15, then x must be equal to 20. So here x is equal to 15. 15 is definitely smaller than 20, but 20 equals to a. So you can write here that 20 equals to a. And from this inequality, x equals to 15 is smaller than 20 and equals to a. We derive that x is smaller than a. Yeah, x is smaller than a. It contradicts our findings that x must be greater than a. Here we have x smaller than a. Due to this contradiction, we cancel the solution. A cannot be equal to 20. So we have only another solution that is left, that a equals to 15. Then x equals to 20. So x equals to 20. 20 is definitely greater than 15. But 15 equals to a, and from this inequality, we derive that x is greater than a. Again, x is greater than a. Exactly the same result, but I only found out that x must be greater than a, x must be greater than a. So the answer to the question is that x equals to 20. Line segment AP is equal to x is equal to 20 units in its length. This is line segment AP. This equals to x, and x equals to 20 units in its length. That is the answer to the second question. So, in the next step, I'll summarize the lecture. We start with the first question. We start with the repetition of the first question, and then repeat on the second question. This second question. First question. Our task is to find out the radius of this circle. This circle blocks this quadrangle ABCD, or quadrangle ABCD is inscribed by this circle. We know that the diameter of this circle is called AC. We also know that side AB of quadrangle ABCD equals to side BC. We also know that the perimeter of this quadrangle ABCD is equal to 18. That is to say the sum of its four side lengths in total is 18 units. AB plus BC plus CD plus DA equals to 18. And the area of this quadrangle ABCD is equal to 16 square units in its size. Again, our task is to find out the radius of this circle that blocks this quadrangle ABCD. So first of all, we define the size of this quadrangle ABCD with names. We define the length of side AB as A. AB equals to BC, therefore BC must be also equal to A. We define the length of side AD as B. We define the length of side DC as C. So in the next step, implement all 7 in our drawing. Okay, quickly on rule 7. According to rule 7, if a peripheral angle subtends on the diameter of the circle, then it is equal to 90 degrees in its side. So in the drawing, we have a circle. This is peripheral angle ACB that subtends on chord AB, that is the diameter of the circle, and therefore it must be equal to 90 degrees in its side. So according to this rule 7, any peripheral angle that subtends on the diameter of the circle must be equal to 90 degrees in its side. This is peripheral angle ABC that subtends on chord AC, that is the diameter of this circle, therefore it must be equal to 90 degrees in its side according to rule 7. Likewise, this is peripheral angle CADC that also subtends on AC, that is the diameter of this circle, therefore according to rule 7, it must be equal to 90 degrees in its side. In the next step, we implement the Pythagoras theorem on those two right triangles. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. In the right triangle ABC, it means that AC square equals to AB square plus BC square. And again, in the right triangle ABC, according to the Pythagoras theorem, we get that AC square equals to AB square plus BC square. AC is the missing hypotenuse, so it is, and it equals to AB square. AB is A, therefore AB square is A square, plus BC square. BC is also A, so BC square is A square. So in total, AB square plus BC square equals to A square plus A square. So AC square equals to A square plus A square, that is 2A square. So according to equation 1, AC square equals to 2A square. In the next step, implement the Pythagoras theorem on this right triangle ADC. According to the Pythagoras theorem, on this right triangle ADC, AC square, that is the square of the hypotenuse, equals to AD square plus DC square. Okay, again, the right triangle ADC, according to the Pythagoras theorem, AC square, that is the square of the hypotenuse, equals to AD square plus DC square. AC is the missing hypotenuse, so we have to set it, and it is equals to AD square. AD is B, therefore AD square is B square, plus CB square. CB plus CD square. CD is C, therefore CD square is C square. So in total, we have found out that AC square equals to B square plus C square. AC square equals to B square plus C square. So we have two equations for AC square. AC square equals to either 2A square or AC square equals to B square plus C square. In the next step, we created equation 3 that says that AC square according to equation 1 must be equal to AC square according to equation 2. AC square according to equation 1 equals to 2A square, and AC square according to equation 2 equals to B square plus C square. So in total, according to equation 3, I have found out that 2A square equals to B square plus C square. Here we divided the equation 3 by 2, and we found out that according to equation 3, a squared equals to b squared plus c squared over 2. The perimeter of this quadrilateral ABCD is equal to 18, that is to say AB plus BC plus CD plus DA equals to 18. AB is A, BC is A, CD is C, and DA is B. So in total, A plus A is 2A, plus C plus B equals to 18. So 2A plus C plus B equals to 18. 2A plus B plus C equals to 18 according to this equation 4. It is given us the question. It is given us the question that the area of this quadrilateral ABCD is equal to 16 squares in its size. Quadrilateral ABCD consists of those two right triangles, and therefore the area of quadrilateral ABCD must be equal to the sum of the areas of those two shapes that it consists of. That is to say, it must be equal to the area of the first shape, that is the area of this right triangle ABC, plus the area of the second shape, that is the area of this triangle, right triangle ABC. So the area of quadrilateral ABCD total equals to the area of the first shape that it consists of, that is the area of the right triangle ABC, plus the area of the second shape that it consists of, that is the area of the triangle ADC. The area of quadrilateral ABCD is 16, so substitute the area of quadrilateral ABCD by 16. What is the area of this right triangle ABC? The area of this right triangle ABC equals to the base AB times the right BC over 2. AB is A, BC is A over 2, so it is A times A over 2. A times A is A squared, so it is A squared over 2. So in total, if you want to know that the area of the first shape is equals to A squared over 2 plus the area of this second shape that is considered of, that is actually the area of this right triangle ADC. It equals to the base AD times the ADC over 2. AD is B, DC is C, so it is B times C over 2. The area of the second shape in total equals to B times C over 2. So in total, according to equation 5, we found out that 16 equals to A squared over 2 plus BC over 2. So here we multiply this equation 5 by 2, and we found out that 16 times 2 is 32, A squared over 2 is A squared, plus BC over 2 is BC. So in total, 32 equals to A squared plus BC, according to equation 5. According to equation 5, we found out that 32 equals to A squared plus BC. A squared plus BC. But according to equation 5, we found out that A squared equals to B squared plus C squared over 2. So we can substitute A squared in this equation 5 by B squared plus C squared over 2. We did it, and we found out that according to equation 5, 32 equals to B squared plus C squared over 2 plus BC. So here we multiply BC by 2, and then we divide it by 2 in order to a common factor with this expression. So we have 32 equals to B squared plus C squared over 2, and 2 times BC plus 2 times BC over 2. So total, according to equation 5, 32 equals to B squared plus C squared plus 2 times B times C over 2. Here we multiply this equation 5 by 2, and we found out that according to equation 5, 32 times 2 is 64. 64 equals to B squared plus C squared plus 2 times B times C. Here we use the algebraic identity that states that A squared plus B squared plus 2 times A times B equals to A plus B squared. So according to this algebraic identity, we get that B squared plus C squared plus 2 times B times C equals to B plus C squared, and it equals to 64. Here we support onto this equation, and found out that the square root of 64 is 8, and the square root of BC squared is B plus C. So in total, B plus C equals to 8. This is according to equation 5, but according to equation 4, we already found out that 2 times A times 2A plus B plus C equals to 18. So we can substitute B plus C in this equation 4 by 8 from this equation 5. We didn't, we found out that 2A plus B plus C is 8 or equals to 18. Here we subtracted 8 from this equation, and we found out that 2A equals to 18 minus 8 is 10. So 2A equals to 10. Here we divided this equation by 2, and we found out that A equals to 10 over 2, that is 5. And again, we found out that A equals to 5 units in its time. this is side AB, this equals to A equals to 5. Side BC equals to A equals to 5, so BC also equals to 5. So AB equals to BC equals to 5. This is actually a right angle that is also an isosceles triangle. So in the next step, we implement the Pythagoras theorem on this right triangle ABC. According to the Pythagoras theorem, in this right triangle ABC, AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. Again, the right triangle ABC, according to the Pythagoras theorem, AC squared equals to AB squared plus BC squared. AC squared equals to AB squared. AB is 5, therefore B squared is 5 squared, that is 25, plus BC squared. BC is also 5, so BC squared is 5 squared, that is 25. So in total, we should found out that AC squared equals to 25 plus 25, that is 50. Here we substituted 50 by 2 times 25. We found out, okay, AC squared equals to 25 times 2. Here we took out of this equation, we found out that AC equals to the square root of 25, that is 5 times square root of 2. So AC in total equals to 5 times square root of 2 since AC is the diameter of this circle, therefore the radius must be equal to the diameter over 2. The radius of this circle, the radius of the open form must be equal to the diameter over 2, AC over 2. That is to say it is 5 times square root of 2 over 2. So the radius of this circle, that is the radius that we are looking for in this question, is equal to either 5 times square root over 2 units in itself. In terms of numbers, the radius of this circle is equal to 3.536 units in itself. So finished to repeat on the first question. In the next step, I repeat on the solution of the second question. This second question is to find out the length of line segment AP is equals to x. We have to find out the value of x. So in the drawing, we have a circle that is described by this right triangle ABC. We know that QS equals to 25, chord QP equals to 24. This is the tangent to this circle, it's point M. SM is the tangent. And our test is to find out the length of this line segment AP is equals to x. We have to find out the value of x. So first of all, we implemented rule 2 in our drawing. Okay, click on rule 2. According to rule 2, the lengths of two tangents for a common standpoint to a circle are equal. So in the drawing, we have a circle. This is the common standpoint point P. For this common standpoint point P, we have two tangents to this circle. Tangent PA and tangent PB. And according to this rule, all two are equal to each other. That is to say, PA equals to PB. On the length of tangent PA equals to the length of tangent PB. So we can implement all two in our drawing. In our drawing, we have this is the common standpoint point A. For this common standpoint point A, we have two tangents to this circle, tangent AP and tangent AQ. And according to rule 2, they are equal to each other. That is to say, AP equals to AQ. But AP is x, therefore AQ must be also equal to x units in itself according to rule 2. We find the length of this short tangent PM as A. From the common standpoint point B, we have two tangents to this circle, tangent BM and tangent BQ. Therefore, rule 2, they are equal to each other. That is to say, BM equals to BQ. But BM equals to A, therefore BQ must be also equal to units in its length. In the next step, we focused on this common standpoint point S. For this common standpoint point S, We have tangent SM, that is tangent to this circle at point M, and we also have here chord PQ, the extended chord PQ touches point S. So all the requirements for 410 are satisfied, and therefore we can implement here rule 10. If we click on rule 10, according to rule 10 is true in any circle, so in any circle, if AB is any chord in the circle, and PT is a tangent to the circle, then the following equation is true, that PT squared equals to PA times PB. Again, PT squared equals to PA times PB. So the drawing in a second, this is the common start point P. From the common start point P, we have tangent PT, that is tangent to this circle is point T. And we have here, this is called PA, the extended chord, this is called VA, the extended chord VA touches point P. So in this drawing, the following equation is true, that PT squared equals to PA times PB. Again, PT squared equals to PA times PB. So as we mentioned before, can implement rule 10 in our drawing. I put in our drawing, we have tangent SM, that is tangent to the circle at point M, and the extended chord PQ touches point S. So all the requirements of rule 10 are satisfied, and therefore we can implement here rule 10. According to rule 10, the following equation is true, that SM squared equals to SQ times SP. Again, SM squared equals to SQ times SP. SM squared equals to SQ times SP. SM is the missing tangent, so we have to set it. And it is equals to SQ, SQ is 25, times SP. SP in total equals to SQ, that is 25, plus QP, that is 24. In total, SP equals to 25 plus 24, that is 49. So in total, we should find out that SM squared equals to SQ times SP. SQ is 25, SP is 49. So in total, we should find out that SM squared equals to 25 times 49. Here we took all to all the little version, and found out that SM equals to the square root of 25, that is 5, times the square root of 49, that is 7. 5 times 7 is 35. So SM in total equals to 35 units in its term. This is tangent SM, it equals to 35 units in its term. What is the left of this transform at SB? SB equals to SM once PM. Yeah, SB equals to SM once PM. So SB in total equals to SM, that is 35, once PM, that is 8. So total SB equals to 35 once units in its term. SM is a tangent to the circle. SM is a tangent, it is absolutely straight line. So if you focus on the upper side of the straight line SM at point B, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles from one side of the straight line is equal to 180 degrees. So which angles we have on the upper side of the straight line SM at point B? We have this angle that is right angle, plus this missing angle, the sum of those two angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its side. So for the other triangle SQB is a right angle. In the next step, we implement the Pythagoras theorem in this right triangle SQB. According to the Pythagoras theorem, SQ squared, that is the square of the hypotenuse, equals to QB squared plus BC. SQ squared, that is the square of the hypotenuse, equals to QB squared plus BA squared. So SQ squared equals to QB squared plus BA squared. SQ is 25, therefore SQ squared is 25 squared, that is 625, plus QB squared, Q equals to QB squared. QB is 8, therefore QB squared is 8 squared, plus SB squared. SB is 35 minus 8, therefore SB squared is 35 minus 8 squared. So in total, we should find out that 625 equals to 8 squared plus 35 minus 8 squared. So 625 equals to 8 squared plus 45 minus 8 squared. So Open the brackets of this expression. 35 minus a square equals to 35 squared, that is 1225, plus a square, minus 2 times 35 times a, that is minus 78. So 625 equals to a square plus a square is 2a square, and we have also minus 78 plus 1225. Here we subtract 625 from this equation, so in this side of the equation we have nothing, that is to say 0, while on the other side of the equation we have 2a square minus 78, 1225 minus 625 is 600. So in total we found out that 2a square minus 78 equals to 600. Here we divided the equation by 2 and finally found out that 2a square over 2 is a square, minus 78 over 2 is minus 45a, and 600 over 2 is 300, 0 over 2 is 0. So in total we found out that a square minus 45a plus 300 equals to 0. So here this is a quadratic equation, and the general formula for quadratic equation is ax squared plus bx plus c equals to 0. Here a, b, and c are the equations of this quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula. X equals to 1 3 plus minus square root of b squared minus 4 times a times c over 2a. In our specific quadratic equation, that is to say a squared minus 35a plus 300 equals to 0, the variable that we are looking for is a. So x equals to a, the coefficient a equals to 1, the coefficient b equals to minus 45, and the coefficient c equals to 300. So we have all the data that is needed in order to find out the variable that we are looking for this quadratic equation a. We just have to put all the data for our specific quadratic equation in this general equation for x, and this way we find out the variable that we are looking for, that is a. So x equals to a. So if we did it, we put all the data here, and we found out that again x equals to a, and it equals to minus b. b is minus 45, therefore minus b is minus 45, that is plus 35, plus minus square root of b squared. b is minus 45, therefore b squared is minus 45 squared, that is 1225. Minus 4 times a times c. A is 1, c is 300, so minus 4 times a times c is minus 4 times 1 times 300, that is minus 1200. So total minus 4 times ac equals to minus 1200 divided by 2a. Divided by 2a. The coefficient a equals to 1, and therefore 2a is 2 times 1, that is 2. So in total, we found out that a equals to 35 plus minus 1225 plus 1200 over 2. 1225 plus 1200 is 25. So inside the outer left only 25. So in total, we found out that a equals to 35 plus minus square root of 25 over 2. Square root of 25 is 5. So in total, we found out that a equals to 35 plus minus 5 over 2. So here we have two solutions that are possible for a. The first solution for a is that a equals to 35 plus minus 5 over 2. 35 plus 5 is 40, and 40 over 2 is 20. So the first solution for a is that a equals to 20. While the second solution for a is that a equals to 35 minus 5 over 2. 35 minus 5 is 30, and 30 over 2 is 15. So the second solution for a is 15. So we have two solutions that are possible for a. A either equals to 20 or 15. In the next step, implemented all 21 in our drawing, but before that we did a construction. This is the right triangle AQP. The right triangle AQP is an associated triangle because side AQ equals to side AP. QP is of course the base of this associated triangle AQP. From point A, we do perpendicular AZ to the base QP. Again, from point A, we do perpendicular AZ to the base QP. So this angle was 90 degrees, and this angle also was 90 degrees according to our construction. So in the next step, implement Rule 21 in our drawing. Repeat question on Rule 21. According to Rule 21, the perpendicular to the base of an associated triangle bisects the base. In the drawing, we have the associated triangle, triangle ABC. Triangle ABC is an associated triangle, put side AB equals to side AC. BC is of course the base of the associated triangle, triangle ABC. From point A, we draw perpendicular AO to the base BC. Again, from point A, we draw perpendicular AO to the base BC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. According to this Rule 21, the perpendicular AO bisects the base BC. Again, the perpendicular AO to the base BC bisects the base BC. So the first half is BO, and it is of course equals to the second half, that is OC, and each half must be equal to BC over 2, because BC has been bisected. So BO equals to OC equals to BC over 2. So you can actually implement Rule 21 in our drawing. Now, because in our drawing we have the associated triangle AQP. The perpendicular AZ bisects the base QP. The first half is QZ. It is of course equals to the second half ZP. Each half equals to QP over 2. So QZ equals to ZP equals to QP over 2 according to Rule 21. And again, according to Rule 21, the associated triangle AQP, the perpendicular AZ bisects the base QP. The first half QZ, of course, equals to the second half ZP. Each half must be equal to QP over 2. QP is 24, 24 over 2 is 12. So from this equation, we got that QZ equals to ZP equals to 12. ZP equals to 12, and QZ also equals to 12. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. So if the size of this angle is alpha, then the size of this angle must be also equal to alpha. So in this adjacent triangle AQZ, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first angle must be equal to 90 degrees minus alpha. 1 plus 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees. It is the sum of the angles in the triangle. Likewise, this point green triangle SQB, this angle equals to alpha, this angle equals to 90 degrees, and therefore this first angle must be equal to 90 degrees minus alpha according to the sum that says that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we prove that those two right triangles are similar to each other according to angle similarity. That is to say, those two angles are both equal to alpha, therefore they are equal to each other. In addition, those two angles are both equal to 90 degrees, and therefore they are equal to each other. And finally, those two angles are both equal to 90 degrees minus alpha, and therefore they are equal to each other. So we can find out that all the fingers of this small green triangle SQB are corresponding equal to all the fingers of this big right triangle AQZ, and therefore those two right triangles are similar to each other according to angle similarity. And from the fact that those two right angle triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that side AQ of this right triangle SQB over side SQ of this right triangle SQB over side AQ of this green right triangle AQZ. It is equal to side QB of this green right triangle SQB or side QZ of this green right triangle AQZ. And again, from the fact that those two right triangles are similar to each other, we derive that the following relationship exists between their sides. We derive that side SQ on the small right triangle QBS over side AQ of the big right triangle AQZ equals to side QB of the small right triangle QBS over side QZ of the big right triangle AQZ. SQ is 25, AQ is X, QB is 8, and QZ is 12. QZ is 12. So total 25 over X equals to A over 12. Here, of course, multiply this equation. If we formula that 25 times 12 is 300 equals to 8 times x. Again, 300 equals to 8 times x. Here we divided this equation by a and find further that x equals to 300 over 8. So we have two solutions to the possible for a. First solution for a, that a equals to 20. The second solution is a equals to 15. We have to find out what is the real solution for a. In order to find out what is the real solution for a, actually, for the drawing here, if the right triangle ABC, if the circle that is inside it in a drawing, and analyze the new drawing in order to find out what is the real solution for A. Is it 15 or 20? So here, this is the right triangle ABC. With the circle that is described inside it, the common from the original drawing. We already found out that AQ equals to X and QB equals to A. So, in the next step, we define the point of tendency of BC with this circle, this point is point M. We define the radius of this circle is R, and we define the center of this circle, this point is point O. So, in the next step, we join points O and M together by straight line. Point O is the center of the circle, point M is the point of the circle itself, therefore OM is the radius of the circle, that is equals to R. The radius of M is equals to R, the radius of M is drawn to point M, that is the point of tendency of tangent BC with this circle. And when your radius is drawn to the point of tendency, then tangent BC will be perpendicular to the radius MO. If BC is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to Rule 1. Point Q is the point of tendency of tangent AB with this circle. We join points O and Q together by straight line. OQ is of course the radius of this circle, that is equals to R, and according to Rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. So in quadrilateral Q, O, and B, we have 1, 2, 3 degrees, and therefore this fourth missing angle must be equal to 90 degrees in size, according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. So in quadrilateral Q, O, and B, we have 4 angles, and therefore it is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in the lower rectangle Q, O, and B, side OM must be equal to the opposite side QB, but OM is out, therefore the opposite side QB must be also equal to R unit in itself. So QB equals to A, and QB also equals to R. The next step, we did a construction, that is to say we extended the radius MO by a straight line until it touches the circle. We define the touching point of the extended radius MO within the circle. This point is point Z. MO is the radius of the circle, that is absolutely a straight line. When you extend the straight line by straight line, the result MZ must be also a straight line. So if you focus on the right side of the straight line MZ point O, here the sum of the angles must be equal to 180 degrees according to Rule 1. So which angles we have the right side of MZ at point O, we have this angle that is the right angle, plus this missing angle, so that the sum of those angles must be equal to 180 degrees according to Rule 3. Therefore this missing angle must be equal to 90 degrees in size. In the next step, we did another construction, that is to say from AB, from side AB, we do tangent to the circle at point Z. Again, from AB, we do tangent to the circle at point Z. We define the touching point of the tangent with side AB, this point is point T. So TZ is a tangent to the circle at point Z according to our construction. But again, TZ is a tangent to this circle at point Z according to our construction. Point O is the center of the circle, point Z is the point of the circle itself, therefore OZ is the radius of the circle, that is equals to R. The radius of OZ is equals to R, the radius of OZ is drawn to point Z, that is the point of tendency of tangent TZ with this circle. And then your radius is drawn to the point of tendency, then tangent TZ will be perpendicular to the radius ZO. If TZ is perpendicular to ZO, it means that this angle equals to 90 degrees according to Rule 1. So in total, if on the other TZ or Q, we have 1, 2, 3 angles, and therefore this fourth missing angle must be equal to 90 degrees in size. So if on the other TZ or Q, we have 4 angles, and therefore it is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in the upper rectangle TZ or Q, side ZO must be equal to the opposite side TQ. but Z0 is the radius of the circle that is equal to R, therefore TQ must be also equal to R. So only found out that QB equals to A and QB also equals to R. QB equals to A and QB also equals to R. What about AQ? AQ equals to X, but AQ equals to AT plus TQ. AQ equals to AT plus TQ. So AQ in total equals to AT plus TQ. TQ is also in total AQ equals to AT plus R. So in total we should found out that AQ equals to X and AQ also equals to AT plus R. Okay, again, AQ equals to X and AQ also equals to AT plus R. AT is the length. AT is the length, it is absolutely positive number. Therefore AT plus R is definitely greater than R because AT is a positive number. So AT plus R is greater than R. And from this non-inequality, we derive that A is smaller than X. Again, A is smaller than X. A is smaller than X, or X is greater than A. So just like I found out that X is greater than A. So we have two solutions for A. A could be either equal to 20 or to 15. We only found out that X equals to 300 over A. X equals to 300 over A. So if A equals to 15, then X equals to 300 over 15, then it's 20. So if A equals to 15, then X must be equal to 20. But if A equals to 20, then X must be equal to 300 over 20, then it's 15. So if A equals to 20, X equals to 15. So here we have X equals to 20. 20 is definitely greater than 15. Again, 20 is greater than 15. And 15 equals to A. Here 15 equals to A. And from this inequality, we will have that X is greater than A. X is greater than A, exactly according to our previous findings, that X is greater than A. So maybe we have two solutions that are possible for A. So we'll check the second solution for A. When A equals to 20, then X equals to 15. So X equals to 15. 15 is definitely smaller than 20. And 20 equals to A. 20 equals to A. 20 equals to A. From this inequality, we derive that X is smaller than A. X is smaller than A. It contradicts our previous findings that X must be greater than A. If X must be greater than A, X cannot be smaller than A. Due to this contradiction, we consider the solution for A. A can never be equal to 20. A, the only solution for A is that A equals to 15, then X equals to 20. So AP equals to X is equal to 20 units in its length. Okay, again, let's found out that this is 9 cement AP, is equals to X, and X equals to 20 units in its length. Okay, thank you very much.